Assalamualaikum, Samad Yaseen, lecture chemistry. BS physical chemistry students, the topic we are going to discuss today is about third order reaction. As you know, those chemical reaction where the concentration terms are raised to power 3 are usually third order reactions. So kinetic equation for the third order reactions can be derived for the three situations where first situation is all the reactants have the equal concentration, second situation where two reactants have the equal concentration, third one is different, and the third situation where all the reactants have the different concentrations. So we are going to discuss first third order reaction with equal concentration of reactant. As you are going to see, three reactants A, B and C are reacted together to form the product. Initially, when rate of T is equal to 0, reaction does not start, product formed 0. After the start of reaction at the time T, formation of product X is going to be subtracted from the initial concentration, and the rate of the reaction dx by dt is directly proportional to the remaining concentration of A, B and C. Hence the final rate equation is dx over dt is equal to k into A minus x raised to power 3. But we know that this equation tells us the progress of the reaction. We are interested, as before, to find out the equation where we can find out the concentration of product or the concentration of reactant at the any given time. For this purpose, as we have done before, we have to integrate the equation 1. For the integration, we are going to separate the variables, taking the variables to the left hand side, and after performing the integration to the right hand side, results are same, kt plus c, but we can see that the left hand side integration is just like the second order integration where a minus x raised to power square. Here just power is 3, formula same. We have to use the formula where the power plus 1, same power plus 1 is going to divide, multiply with the multiples. As a result, we are going to get the final form of equation 1 over 2 a minus x square is equal to kt plus c. You know, c is the integration constant. We want to find the integration constant by putting the boundary condition x is equal to 0, t is equal to 0. By putting the boundary condition, we are going to get c value of 1 over 2a square. By putting the c value in the equation 2, the final form of equation is 1 over 2a minus x square is equal to kt plus 1 over 2a square. This is a straight line equation where y is equal to mx plus c. We are going to plot a graph between the time, which is independent variable, against 1 over 2 a minus x square on the y-axis. Hence we get a straight line with the intercept showing 1 over 2 a square, and the slope value is usually represented a rate constant. We can rearrange the equation 4 by taking the variables to the right hand side. As a result, equation will be kt is equal to 1 over 2 a minus x square minus 1 over 2 a square. You are going to take the LCM of this of this right hand side of equation, and in the next step we are going to open up the square a minus x whole square, and after cutting these some values we are going to get the equation kt is equal to 2ax minus x square divided by 2a square into a minus x whole square. You can take x common from the upper side of an equation, so the equation will become kt is equal to x into 2a minus x divided by 2a square into a minus x whole square. Then you are going to find out the rate constant. You can take the time to the left hand side to the right hand side. As a result, you are going to get the equation. In this equation, if you are going to put at different time interval value of x and get the consistent results, mean your equation is considerably in agreement with the third order. Now equation 5 can be written as above: kt is equal to x into 2a minus x divided by 2a square into a minus x whole square. This is again equation straight line without intercept. We are going to plot a graph between the time and whole portion present on of the equation on the left hand side. there is the straight line passing through the origin, and the slope of the line give us the rate constant as before. Now next heading is unit of third order rate constant. We have to find out the third order rate constant units by the equation number 5. Put up the values of x, a minus x and t. You know the value of x, concentration mole per dm cube, time second. Then after cutting the different units, we are going to get the final equation for the rate constant units, dm6 per mole square per second. Now next heading is half-life period of third order reaction. You know, for the half-life, to finding out the equation for the half-life, we have to put up the t is equal to t half and x is equal to 0.5a or 1 by 2a. We are going to put these t with t half. We are going to replace the t with t half and x with 0.5a, and after simplification you are going to get the equation 3 by 2 ka square is equal to 1.5 ka square. Means half-life of the third order reaction is inversely proportional to the square of the initial concentration of reactant. So now we are going to see the third order reaction when the initial concentration of two reactants are same and third one is different. Suppose again three species A, B, C are reacting together to form a product. Here two species A and B have the equal concentration A mole per dm cube, while third one is different, B mole per dm cube. Again, after the start of reaction at the time t, x amount of product is formed, then the rate law dx over dt is equal to k into a minus x whole square into b minus x. So again this equation give us the progress of the reaction. We want to find out the equation to which tell us the remaining amount of reactant and the formed amount of product at a given time. We have to integrate the equation 1. We integrate this equation by separating the variables as we have done before. So right hand side of equation will give us the same result, while the left hand side of the equation we cannot solve it by the simple integration rule or method. We have to apply the partial fraction method, which we have applied for the second order reaction when the concentration of reactants are different. As a result, we get the final form of equation in the as represented at third equation. So this equation is also straight line equation, which is without intercept. You have to plot a graph between time and the whole portion present on the left hand side on the y-axis. As a result, you are going to get a straight line passing through the origin, and slope of this line is going to give us the rate constant. Similarly, third situation where third order reaction have the initial concentration of all reactants are unequal or different from each other. Here again A, B, C, three species are reacting together to form the product. All three species have the different A mole per dm cube, B mole per dm cube and C mole per dm cube concentrations. So after starting the reaction at the time t, we are going to get the rate equation dx by dt as represented k into a minus x, b minus x into c minus x. Here again this equation tells us the progress of the reaction. We want to find out the equation which tell us the remaining amount of the reactant present at the time t. For this we have to integrate it, and we cannot solve it by the simple integration method. We have to follow the partial fraction method. So after partial fraction method we have to find out the integration constant, and doing all these steps as we have done before, we get the final equation as represented in this second equation. So again this is a straight line equation without intercept. We have to plot a graph between the time t and whole portion of the equation present on the left hand side. We get a straight line passing through the origin give us the rate constant. So the slope of the line give us the rate constant as we have studied before. Now interesting examples of the third order reaction. As you know, nitric oxide when oxidized give us the nitrogen dioxide. This process as you seen is going with the decrease the number of mole is directly proportional to pressure in gaseous form. Hence this reaction can be monitored by the pressure apparatus manometric method, and we get the same equation as we have studied for the third order reactions. In the second example, where ferric chloride react with the stannous chloride to form us ferrous chloride and the stannic chloride, in this equation actually iron is going to be reduced and tin is going to be oxidized. So this oxidation reduction reaction, we have to monitor this reaction with standard oxidizing agent potassium dichromate solution. Similarly, third order reaction in gas phase, where nitric oxide react with hydrogen to form nitrous oxide and water. Similarly, formation of nitrosyl chloride and nitrosyl bromide, an example of third order reaction in gas phase. Third order reaction in solution phase, where ferric chloride solution react with potassium iodide solution to form the ferrous iodide, potassium chloride and iodine. Likewise, hypobromous acid in an 6.4 to 7.8 pH range decompose to give us HBr and hydrobromic acid. Likewise, sodium formate react with silver acetate to give us metallic silver along with carbon dioxide, acetic acid and sodium acetate. Here actually silver is going to be reduced. Now very important topic, methods to determine the order of reactions. As we know that order of reaction cannot directly calculated from the balanced chemical equation. Sometimes for the elementary reaction it could be, but mostly it should be find out by the experimental reactions, because the exact mechanism of reaction actually give us the order of reaction. So there are different methods to find out the order of reaction. First method is method of hit and trial, where we are going to collect the data in the laboratory. After performing an experiment, we are going to get the readings for the different concentration of concentrations and reactants. Concentration is going to be decreased and product is going to be increased at the different time intervals, and these values are going to be put in the first order reaction as represented in first point. If the rate constant comes out to be constant values, means this reaction is first order. If the values of rate constants are not constant, we are going to put this data in the second order equation as given in the point 2. And if we get the rate constants values similar, then this is second order reaction. If also rate constant does not give us the similar values for the different datas, then we are going to put this data into third order equations and reaction will be third order. So this is called method of hit and trial. It is usually popular before. Now it is only used for the simple reaction. Complex reaction, this is not followed. Now next method is graphical method. As we know that as the chemical reaction is going to proceed, with the passage of time, reaction progress is going to be decreased, mean amount of product with the passage of time is become less and less, mean product is going to be increased but its rate is going to be decreased. So we are going to plot a graph between time and concentrations, time on x and the concentration on y axis. Then the curve is obtained, and the curve, from the slope of the curve we can get the rate of the reaction dx by dt. So dx by dt for the first order reaction as represented k into a minus x. So here a minus x is an if we are going to plot a graph and this first order equation representing a straight line equation without intercept, so a minus x will be an independent variable and dx over dt rate is going to be dependable. Basically rate is going to depend upon the remaining concentration of the reactant. So graph is plotted, straight line passing through the origin without intercept, and the slope of the line give us the rate constant. Similarly, second order reaction equation represented dx over dt is equal to k into a minus x whole square. Again this is straight line equation without intercept. We are going to plot a graph between a minus x square into dx, and the rate of the reaction gives a straight line passing through the origin, and the slope can be calculated and by the tan theta, which give us the rate constant. Likewise for the third order reaction we are going to treat it similarly and get the same results. Now third method to determine the order of the reaction, half-life method. As we know that half-life equation for the different order of chemical reactions can be find out, and we have find out in the previous lectures. For the first order reaction, the half-life equation shows that it is independent of the initial concentration of the reactant. For the second order reaction, is shows that it is inversely proportional to the initial concentration of reactant, and for the third order reaction, it is inversely proportional to the square of the initial concentration of the reactants. So after careful look after careful looking all these half-life equations of the different order of the reaction, we can find out this result that actually half-life of any nth order of reaction is inversely proportional to the initial concentration of the reactant, one less than the order of reaction. Means whatever the order of reaction, you have to one minus from that order of the reaction to get the inversely proportional equations for the half-life equations. Suppose we have one situation where we have the two half-lives T1 and T2. These half-lives for the two different concentrations A1 and A2. So two equations can be written for this. First equation, T1 inversely proportional to 1 over A1 raised to power n minus 1, and similarly equation 2. So we are going to divide equation 1 by equation 2. We are getting it T2 over T1 is equal to A1 over A2 raised to power n minus 1. This is simple mathematical treatment where we are going to divide the equation 2 by 1. Left hand side is simple division, while the right hand side, when going to divide, similar power is going to be combined. Now to find out the order of reaction n in the given equation, we have to just simplify this equation as such that we are going to take a natural log ln on the both hand side of an equation, where after taking the natural logarithm, we are opening the formula of natural logarithm of the right hand side. You can see that power n minus 1 comes before the logarithm. This is just logarithmic mathematical formulas. The power comes before the values. So in the next step, we are going to separate the n minus 1 and taking the log of a1 over a2 to the other side by the division. So final form of equation will be n is equal to the log of t2 by t1 divided by log of a1 by a2 plus 1. So hence this final form of equation tell us that we can find out the order of a reaction if we know the two half-lives and the two concentrations, initial concentrations. Then order of reaction can be calculated. Likewise, fourth method to find out the order of reaction is differential method. Actually, Van Hoff has find out this method, so it is called Van Hoff differential method. If we know the rate of reaction, as we know that rate of reaction is directly proportional to the concentration of reactant raised to power whatever power 1 2 3 it is represented by n. Hence, if C is the concentration of reactant at any time t, the rate of the reaction respect to C can be written in the form of rate of the reaction minus dC over dt is equal to K into C raised to power n. So we are now again applying some situation that there are two experiments are going to be performed. Two different concentrations give us the two different rates. So first rate dc1 by dt and second rate dc2 by dt. Now this equation 1 and equation 2, we are going to take the common log of these two equations. So after taking the common log, we are going to see that the right hand side of equation is going to be simplified by the simple logarithmic opening formulas. Two multiplied factors going to be added and the power factor is going to be come before the initial value. So after subtracting the equation 4 from equation 3, we are going to rearrange it. Just log of k value is going to be cancelled out and the final form of equation will be n is equal to log of dc1 by log of rate of first concentration minus log of rate of second concentration divided by log of first concentration minus log of second concentration. So in order to find out the order of reaction by the want of differential method, we must have two different rates at two different concentrations. Rate of the reaction, you know that we can find out by the different curves. Now last method to find out the order of reaction is Austral isolation method. It can also be called large excess method. Actually this method is employed for the complex reactions. For example, we have the three reactant A, B and C are reacting together to form the product. So overall order of the reaction will be dependent upon the individual orders of A, B and C. So what we do, we will isolate the one reactant from the other two reactant by taking the other two reactant in a very large excess. For example, we are going to take the B and C in a large excess, then rate of the reaction will be only dependent upon the A. But because the reactant which is present in a very large amount does not affect the rate of our reaction, so we are going to find out the rate of reaction with respect to A. Similarly, when we had the reaction rate with this reaction rate and find out the order with respect to A, then again we are going to apply the situation with B. We are going to find out the order of B by taking the reactant A and C in an axis, and we are going to find out similarly order with respect to A and A, B and B, and order of C is NC, and overall order of reaction will be Na plus Nb plus Nc. Individual order of reactants are added up to get the overall order of the reactions. Students, now experimental techniques to follow the reaction rates. What are the experimental techniques are applied to calculate or find out the reaction rates? Different techniques are employed. We have to pick up the technique depending upon the different conditions, which technique suits our optimum conditions. To find out or record the progress of data mean we have to find out the concentration of reactant and product at different time intervals. Actually, which analytical technique you are going to select for taking the data, it depends upon the half-life of a reaction and also the time scale upon which the method operate. Now whichever technique or method you have selected for taking the data for the reaction rates, it should have some properties or features upon which its selection will be done. First, technique should be fast, instantaneous, rapid. It should record the concentration changes very efficiently, and similarly last, these techniques should not be influenced by the rate of reactions, mean their reliability is their reliability should not be changed with the slower reaction or a faster reaction. Now different type of sampling techniques are employed: direct sampling techniques and the indirect sampling techniques. The indirect method, direct sampling techniques. In this technique, actually we are going to perform actual experiment, and at a particular time, when t time of the experiment is gone, at the given t time we are going to pick up a small volume or aliquot from the given reaction mixture, and we are going to arrest the reaction mixture at that point for a suitable technique by cooling it or by adding some suitable additive to it, and find out the concentration of remaining reactant or a formed product. Likewise, indirect sampling techniques, where we are not directly measuring the concentration of reactant and product as in the direct sampling techniques, we are going to find out some property of the substance which change with the concentration of the product or a reactant by change. So we are going to calculate that property of, and that property is directly proportional to the concentration of reactant or a product. These mostly physical properties which are employed in the indirect sampling techniques are volume changes, enthalpy changes, density, optical rotations, conductivity, potential measurement, polarography, spectroscopical techniques, magnetic properties measurement, and similarly refractive index measurements. Study of fast reactions. Students, some reactions are so fast that kinetically their determination and collection of data requires some special techniques, some special methods such as relaxation method, flash photolysis method, and molecular beam method. Thank you.